Good evening everybody and welcome to Analog Electronic Circuits. This is lecture 15. In the last class we looked at the voltage controlled current current controlled voltage source, where the incremental picture looked like this. This is IN, this is RL, and if you assume that the current source has some internal resistance RS, then if Gm tends to infinity, what comment can we make about the input resistance? Input resistance seen by the source here is 0. What comment can we make about the incremental voltage there? Incremental voltage there is 0. What comment can we make about the incremental current flowing there? IN. What comment can we make about the incremental voltage there? IN times R. What comment can we make about the incremental current flowing here? Very good. Why? Because this the output voltage is IN times R. So, the current flowing in the load is IN times R over RL. So, what is the current flowing in the transistor? Yeah, it is flowing in the opposite direction. If you want to avoid the negative sign, that current is nothing but IN times 1 plus R by R. Sanity check: if RL tends to infinity, all that current must flow into the transistor. So, does it make sense? What comment can we make about R out? When Gm is infinity, it is 0. And so, what is the meaning of large Gm? Gm must be much larger than 1 by Rs and 1 by R. Okay. So, with that refresher, now we are going in a good position to, this is the incremental network. We are now in a position to make the real thing, and that is, again, you pick your favorite biasing scheme, right. I am going to pick I do not know, something, for example, all right, let me just pick something with gate voltage is constant, we measure at the source, feedback at the source, we use a poor man's current source, and this is the VDD. So, this is R2, this is R1, and this is some Rx. And the job of Rx is to reduce the, why do we have Rx there? Yes, why do we have Rx there? Huh? To reduce what? How can adding a resistor in series with the source reduce its voltage? Can somebody give me a more coherent answer? Yes, Ralph. Yeah, so basically the Rx basically attempts to do whatever it takes to keep the current in the transistor constant. Of course, it works only when Rx is large, and what is the meaning of Rx being large? What is a large Rx? Pardon? Yeah, Rx should be much larger than 1 over Gm. Okay. With all those conditions satisfied, I mean this stabilizes the bias current pretty well. Alright, so now we need to make the incremental network look like the one shown on top. So what do we do? Okay, so IS, RS, straightforward. Okay, what else? So the load, there are multiple ways of doing it. One is to just put it in the drain. All right. What else? The source must be, yes, grounded. So what do we do? Put an infinite capacitor. All right. Are we done? In the incremental network, we see that the drain and the gate are connected to a resistor R. So what do we do here? Okay, so that's a transistor. Yes. So what do we do with R? Okay, one way of doing it is use an infinite capacitor. Put R. Okay. What happens if I don't put a capacitor? Yeah, depending on the choice of R1, R2 and RL, right, current could flow between through the resistor R and thereby disturb the operating point of the transistor. Okay. All right. So this is basically perfectly working current controlled voltage source, and nothing basically as we discussed the last time. If this is Vi and this is Rs, as Gm tends to as Gm becomes very large, what comment can you make about the incremental voltage at the output? What is the incremental voltage at the output? Minus R by Rs times Vi. Okay, I hope that's apparent. Okay, we spent a lot of time in the last class. All right, so basically, I mean, if you want to impress your friends, you can draw a big circuit like this, right? And you can, by simply staring at the picture, without doing any math, right? You can be sure that the gain is going to be approximately minus R by Rs. Even though this the circuit looks quite complicated with half a dozen resistors and a few capacitors and so on. All right. Okay, so that covers the current controlled voltage source.